All right, let's dig into a truly mind-bending question. What if our entire universe, with all its galaxies, stars, and, well, everything you see and touch, is actually just a projection?
Like a cosmic hologram.
Exactly. It sounds like something
Mhm.
straight out of a blockbuster movie, right? But for the last 25 years, physicists have been exploring an idea that suggests exactly that.
Yeah, you're talking about the holographic principle and specifically the ad-SCFT duality conjecture, anti-de Sitter conformal field theory.
Right.
It was first proposed by Juan Maldacena about a quarter century ago, and it was, well, some called it a magical statement.
A magical statement. I like that.
Because the core idea is that our 4D spacetime, the one we live in, could be a holographic projection, a projection of a lower dimensional reality.
Okay, like how a 3D hologram emerges from just a 2D surface.
Precisely like that.
So our mission today is to take a deep dive into this, well, frankly, bizarre and counterintuitive idea. We're going to unpack how physicists are using it to tackle some of the biggest mysteries out there.
You mean things like black holes, the nature of space-time itself.
Exactly, and even the very, very early universe right after the Big Bang. And you'll discover why this duality, even though it sounds shocking, has actually held up really well under scrutiny.
And why it offers this powerful new lens, really, to view reality.
Okay, so to really get it, let's start with the core idea, the duality itself. What did Maldacena actually find?
So Maldacena found that a five-dimensional theory of anti-de Sitter space ADS, for short, that theory included gravity.
Right, gravity's in there.
And he found it could describe the exact same physical system as a different theory, a lower dimensional quantum field theory, a CFT, which is all about particles and fields, but crucially, without gravity.
Okay, hold on. Let's pause there because that sounds fundamentally contradictory. How can two theories, one with gravity, one without, one with more dimensions, one with fewer, how can they possibly describe the same physics?
It's a huge conceptual leap, absolutely. The bridge is the mathematical equivalence. Think of it like having two completely different languages, maybe English and French.
Okay.
They sound different, different grammar, everything, but they can express the exact same meaning.
Yeah,
right?
okay.
The duality suggests these two theories are just different mathematical languages describing the same underlying reality. And the real power, the key insight, is this idea of simplicity through equivalence. Meaning sometimes you have a problem that looks impossible in one theory, say the gravity one, but you translate it into the other language, the CFT one, and suddenly it's simpler, maybe even solvable.
So it's like finding a mathematical backdoor to solve really tough physics problems. That's a huge practical advantage.
Exactly.
But it still sounds almost like a bolt from the blue. Where did Maldacena even get the first hints for this? What inspired him?
Well, like most big ideas, it didn't come from absolutely nowhere. He was heavily inspired by earlier work in string theory, particularly Joseph Polchinski's work on D-branes.
D-branes. Okay, refresh my memory on those.
Think of them as sort of sticky surfaces or membranes within string theory where strings can end. Polchinski showed these D-branes had two very different descriptions that were equally valid.
Two descriptions?
Yeah. One described them using gravity as massive objects warping space-time. The other described them using quantum field theory, just the particles and forces living on the brane itself. No gravity in that description. That hinted at this kind of connection.
Okay, so Polchinski had this duality for a specific object, the D-brane. How did Maldacena make the leap to entire universes?
He spotted some crucial similarities, both the quantum field theory on the branes without gravity and the ADS theory with gravity and an extra dimension. They were both scale invariant.
Meaning their physics looks the same no matter how much you zoom in or out.
Exactly. A very powerful symmetry. And the lower dimensional CFT also had something called conformal invariance. Its laws don't change, even if you stretch or squash things, as long as you preserve angles.
And ADS space had similar symmetries.
It did. As Maldacena himself said, the fact that these two theories have the same symmetries was an important clue. It wasn't just a coincidence.
Okay, that's a strong clue. But there was another piece, wasn't there? Something about how strongly the particles interacted.
Absolutely. That was maybe the stroke of genius. The quantum field theory, the CFT side, was strongly coupled.
Meaning particles interact really intensely, like a messy, chaotic system.
Yeah, think of a super crowded party, interactions everywhere, incredibly hard to calculate anything precisely. But the other theory, the ADS gravity theory, was weakly coupled.
So particles interacting much more gently, easier to track.
Much easier, like a quiet coffee shop versus that chaotic party. And crucially, it was an inverse relationship. When one was strongly coupled, the other was weakly coupled, and vice versa.
Ah, so you could do the easy calculations in the weakly coupled theory.
And the results would tell you exactly what was happening in the seemingly impossible strongly coupled theory.
It's like having a universal translator for physics problems. Okay, so how did people react back in 97 when he proposed this? Must have seemed, well, nuts.
It did seem pretty wild. Took a while to sink in. Physicists apparently wrote hundreds, thousands of papers just checking it, checking every little detail because at first it just seemed so ridiculous.
That a theory without gravity could somehow be the same as one with gravity?
Exactly. But remarkably, the maths held up. The duality passed test after test. And pretty soon, theorists realized they could use it to tackle some really long-standing, confounding puzzles.
And one of the biggest ones has to be the black hole information paradox. I remember learning about Stephen Hawking's discovery back in the 70s. Black holes aren't totally black.
Right. They emit thermal radiation, Hawking radiation, and they evaporate over immense timescales.
But that immediately raised a huge red flag for quantum mechanics. If the black hole disappears, what happens to the information about everything that fell into it? Quantum rules say information can't just be destroyed. So where does it go?
This is precisely where ADAS-CFTs started offering really compelling answers. In 2006, Shinsei Ryu and Tadashi Takanagi made a key connection.
What did they find?
They used the duality to link the area of a special surface inside the ADAS wall black hole. It's called an extremal surface. Think of it as a specific boundary within the geometry.
Okay.
They linked the area of that surface to something called entanglement entropy in the partner CFT system.
Entanglement entropy, that measures how much different parts of a quantum system are linked, how much they know about each other.
Exactly. It's a measure of quantum correlation. So Ryu and Takanagi showed geometry on the gravity side, the area, was directly related to quantum information on the field theory side, the entanglement.
So their work suggested that as the black hole evaporates in ADAS, the area changes, and this matches the entanglement entropy change in the CFT. And since the CFT obeys quantum rules,
information must be preserved. It looked like a major breakthrough for the paradox. But there was a slight hitch.
Oh, what was that?
That initial Ryu-Takanagi formula, it was brilliant, but it didn't fully incorporate the quantum effects that actually caused the black hole to evaporate in the first place.
Ah, okay. So it was close, but not the full story.
Right. The real clincher came later. In 2014, Netta Engelhardt and Aaron Wall figured out how to calculate the area of what they called a quantum extremal surface, which did include those necessary quantum corrections.
And that calculation worked.
It led to the final piece. In 2019, Engelhardt and others confirmed that using this quantum extremal surface area lets you track the entanglement entropy of the Hawking radiation itself in the CFT.
And does it follow the rules? Does information get conserved?
Perfectly. It follows exactly the curve predicted by quantum mechanics if information is conserved. It provided this amazing geometric litmus test showing information isn't lost, something we could likely never have figured out without the duality framework.
Okay, this connection between quantum entanglement in the CFT and spacetime geometry in ADS, it leads somewhere even more radical, doesn't it?
It really does. It leads to this absolutely astonishing idea. Maybe space-time itself isn't fundamental. Maybe it emerges from quantum entanglement.
Emerges, like the fabric of reality itself is woven from quantum connections. That sounds profound.
It is. Think about it with an analogy. Imagine you have just a few water molecules floating around as a really dilute gas.
Okay, just bouncing around randomly.
Right. You can't really describe that gas using fluid dynamics, right? There's no flow, no waves. It's just individual molecules.
Just fence.
But now, let those molecules condense. They get close, interact, form liquid water. Suddenly, hydrodynamics emerges. Flow, pressure, waves. These are collective behaviors that weren't there before.
So the complex behavior, the hydrodynamics, emerges from the simpler interactions of many molecules. How does that map to spacetime?
Well, something strikingly similar seems to happen in ADAS-CFT. On the CFT side, the quantum side, if you have subsystems with zero entanglement between them,
No connection.
no connection, then the corresponding description on the ADS side, the gravity side, has no connected space-time. There's nothing for general relativity to even describe. It's like space-time isn't stitched together yet.
Wow. So what happens when you add entanglement?
As you increase the entanglement between different parts of the quantum system on the CFT side, patches of space-time start to, well, emerge in the ADS description.
Mm.
They might even be disconnected at first.
Little islands of spacetime appearing?
Sort of. And then, if you crank up the entanglement even more, make the quantum subsystems really strongly linked.
Then the patches connect.
Exactly. These patches of spacetime link up, they merge, and eventually they form a smooth, continuous volume of spacetime like the kind Einstein described.
So this implies the underlying quantum system, the CFT without gravity, is somehow more fundamental, more real than the spacetime we experience.
In a very real sense, yes. It's like the 2D surface is more fundamental than the 3D hologram it projects. Take away the entanglement in the quantum system.
And spacetime disappears.
Exactly. As one physicist put it, take away all the entanglement and then you just eliminate the spacetime. It's a derived property, an emergent phenomenon.
This whole idea points directly at one of the biggest goals in physics, finding a unified theory of quantum gravity. We've got general relativity for the big stuff, quantum mechanics for the small stuff.
And for over half a century, putting them together has been the ultimate challenge. They just don't seem compatible in extreme situations, like inside black holes or at the Big Bang.
So how does holography help bridge that gap?
It provides a crucial insight. The success of ADS CFT strongly suggests that any successful theory of quantum gravity is probably going to be holographic in nature.
Meaning it will have this dual description, a lower dimensional version without gravity, like the CFT.
That seems to be the implication. It doesn't hand us the final theory on a silver platter, of course, but it gives us a powerful guiding principle, a blueprint for what that theory should look like. It tells us what kind of mathematical structure we should be searching for.
And people are already using this framework to tackle things like the very early universe. You mentioned inflation earlier.
Yes, absolutely. People like Horatio Estes are using AD-SCFT to model the state of the universe during inflation, that incredibly rapid expansion just fractions of a second after the Big Bang.
Which would normally be impossible to calculate directly, right? Because it was so hot and dense.
Exactly. It was a strongly coupled, high-energy plasma. Very messy. But using the duality, you can translate that problem to the weakly coupled CFT side.
Making the calculations manageable.
Making them tractable, yeah. Nastas's work suggests the early universe could be described as this strongly coupled fluid, and its behavior, translated via the duality, matches features of the expanding universe we see.
Does it connect to actual observations? Can it predict anything?
Well, with some tuning of the model's parameters, it can actually replicate things we do observe, like the tiny temperature fluctuations in the cosmic microwave background radiation.
The leftover heat from the Big Bang.
That's the one. Those tiny ripples were the seeds of all the galaxies and large-scale structures we see today. So yes, it's showing real promise for connecting theory to observation, even for the very beginning of time.
The implications are just staggering. But let's be realistic, like any theory, especially one this weird, there must be challenges, right? Applying it to our specific universe.
Oh, definitely. That's a huge caveat and a major area of research. The big one is the AGS versus our universe problem.
Meaning the anti-de Sitter space in the duality isn't quite like the space we actually live in.
Exactly. AGS space is a specific mathematical solution in gravity theory. It's negatively curved, kind of saddle-shaped, and it's asymptotically empty in a particular way. Our universe, observationally, seems to be much closer to what's called de Sitter space.
Which is different how?
It's expanding, accelerating outwards, and on large scales it appears spatially flat, not negatively curved like 8S.
Yeah.
And it's certainly not empty. It's filled with galaxies.
So the specific mathematical setup of ADS-CFT doesn't directly map onto our observed cosmos.
Not directly, no. The big push now is to find a similar holographic duality for de Sitter space, one that would describe our universe.
Is there a leading candidate for that?
Not yet, honestly. There are ideas, proposals, lots of active work, but no clear consensus on a DSCFT yet. But physicists are optimistic that the holographic principle itself is general, even if the specific AD-SCFT example isn't the final word for our universe.
Given that we're talking about quantum gravity, energies far beyond particle accelerators, how on earth do you even test something like the holographic principle?
That's the tricky part experimentally. Direct tests are incredibly difficult, maybe impossible with current tech. But for theoretical physicists, their experiment is often the mathematics itself.
How so?
As one group at Utah State put it, a precise mathematical model is akin to the apparatus of an experimental physicist. They use the holographic principle, the AD-CFT duality, as their theoretical apparatus.
To make predictions.
Exactly. They use it to predict properties of quantum gravity, check for mathematical consistency, see if it resolves paradoxes like the information loss problem. And they look for connections, even indirect ones, to things we can potentially observe, like those cosmic microwave background details.
It really makes you reconsider everything, the potential impact if this holographic idea is fundamentally true. It's hard to overstate. Mark van Ramsdonk, who's done key work on the entanglement connection.
Right, he put it very powerfully. He said, if our universe does have an underlying holographic description, then understanding this duality.
We'll be at the level of understanding quantum mechanics, at the level of understanding general relativity.
Yeah. He said it would be as big of a leap in our understanding of the universe as anything else that's happened in the history of physics. It fundamentally shifts your perspective on what's real and what's emergent.
So let's recap this deep dive then. We've seen how the holographic principle, especially through ADA-CFT, offers potential solutions to the black hole information paradox.
How it strongly suggests that spacetime itself might not be fundamental, but instead emerges from the entanglement of a lower-dimensional quantum system.
And how it provides a powerful framework, maybe even a necessary ingredient for any future theory of quantum gravity, helping us probe even the earliest moments of the universe.
It's an incredibly audacious, elegant, and yes, bizarre idea that has reshaped theoretical physics over the last 25 years.
Absolutely. And it leaves you with this final, really provocative thought. If our universe truly operates like a hologram, if spacetime is just an emergent feature, what does that actually mean for our perception of reality?
What part of nature is genuinely fundamental, truly real, and what aspects are just a magnificent, intricate illusion arising from something deeper and perhaps much simpler? It certainly gives you a lot to think about regarding the nature of existence itself.